So it's my pleasure to have Dr. Parzygnat from the IHES as the speaker of our seminar today. Dr. Parzygnat is a leading expert in quantum probability, but he also working in other fields of mathematics like algebraic topology or functional analysis. The title of his talk today is a categorical approach in quantum probability. Please, Arthur.
Thank you. Thank you for the introduction, and also thank you for the invitation to this seminar. So I will start right away, and I'll talk about a categorical approach to quantum probability and sort of the interplay between recent advances in categorical classical probability theory and how these things apply in the quantum context, or how you can try to see what aspects of quantum probability can you actually see from this perspective. And this is sort of like an open talk, so feel free to ask questions at any point in time. I'd rather have more of a discussion rather than just a monologue. So I think it's more important that you get something out of this than nothing. So I'll just, this is sort of a rough outline of my talk. I'll briefly mention some examples of finite dimensional C-star algebras and positive maps and positivity, and why that is an important role and how it relates to probabilities. I'll also briefly talk about almost everywhere equivalence, a non-commutative generalization of almost everywhere equivalence, and what Bayesian inversion is in a setting that applies equally well to classical probability, but also non-commutative probability. And then I'll talk about how you can use Bayesian inversion in an updating procedure to update hypotheses based on evidence. And I'll give an example in the classical setting. I'll spend a lot of time on that one just because I think it's a very good illustration of how it's used if you've never seen it before. And I'll also talk about the Einstein-Podolsky-Rosen example or experiment, you could say a thought experiment, in terms of quantum Bayesian updating. And I'll also mention a quantum Bayes theorem that my collaborator Benjamin Russo and we proved together, and also recently expanded this theorem to include a lot of ideas from modular theory in C-star algebras and von Neumann algebras with Alessio Ranallo and Luca Giorgetti. And then I'll talk about special cases of Bayesian inversion, which are called disintegrations, and how they're related to things like conditional expectations and also error correction. So just to start off, I'll also write down what a C-star algebra looks like. And I don't want to give the full general definition and talk about all its properties, but some of the structure that it has is that it's an algebra with a unit over the complex numbers. You have an involution, and we generally depict these operations, or at least some of these operations, string diagrammatically. So I've drawn like what the multiplication looks like. You take two elements, and then you combine them to get a new element in your algebra. There's a unit because we have unital algebras, and I'm going to be always working with unital maps, unital linear maps, or conjugate linear maps. And those always send the unit of the complex numbers into the unit of your algebra. So there's always a unique map. And because it's unique, we sometimes draw it as like a grounding operation. And I'll be reading these diagrams from top to bottom. And if you're a physicist and you're wondering like, how do I interpret this? If you're reading it from top to bottom, you're in the Heisenberg picture. And if you're reading these string diagrams, whenever I write them from bottom to top, you're in the Schrodinger picture. And there's also an involution, which I wrote on the right, which I'll just briefly mention a few times throughout the talk. So some examples are things like the complex numbers, with the usual complex conjugation, multiplication, and the norm, absolute value. You can also take complex valued functions on any finite set and just take the sup norm. This is just like a direct sum. So it's kind of like a vector space with the algebraic structure of just pointwise multiplication. You can also do something a little bit more fancy, which is if you have a complex Hausdorff space, you can take continuous functions from that space into the complex numbers, and that also forms a unital C-star algebra. And those are all commutative examples. If you want a non-commutative one, a good place to start is with a matrix algebra. So square matrices of any dimension with the complex conjugation, the conjugate transpose as the involution, and matrix multiplication as multiplication. And there's also a norm, which is the operator norm. You can also kind of combine the second example with the fourth example by sort of taking a direct sum of matrices, of matrix algebras, and a situation, another way to view this is to think of saying, like, I have a function on a space X into different matrix algebras. So you associate to each point on your space X a matrix, and the set of all of those maps form this direct sum. So these are some of the basic examples I'll be working with throughout the talk. I won't be really dealing with infinite dimensional ones except the third example. So there won't be any infinite dimensional, strictly non-commutative algebras in this talk. And if infinite dimensions is all you care about, then you might as well, you might think, oh, you know, there's no reason for me to stay here. But, you know, having, like, you know, some background in quantum information theory, I would argue that, you know, that's not always the case. There are a lot of interesting questions in finite dimensions that you could ask that are still unknown. You know, they're still open. So there are very special elements inside of algebras that we want to isolate, and these are called positive elements. Now, positive elements are always of the form A involution A. So what are some examples? Well, in C, these are just the non-negative reals, right? If you take a complex number and then you square it in this way, z conjugate z, then that gives you its absolute value squared, and that's a non-negative number. For functions, these are just non-negative functions. So at every point, they give you a non-negative number. For matrices, it's a little bit different. You have that a matrix is positive if and only if it's satisfies two properties. First, it's a self-adjoint matrix, and second, its eigenvalues are non-negative real numbers. So it's very important that it's self-adjoint, because if you look at this form that this matrix is in, and you take its and you apply the conjugate transpose to that, you get back exactly the same thing. So in order for these two things to be equivalent, you really need this self-adjoint assumption. And for direct sums, then you can think of this as pairs, or not pairs, but tuples of positive matrices. And what do we do with positive elements? Well, one of the things, we'll relate them to states and probability distributions in a moment, but we also want to be able to know what happens when you apply operations to positive elements and where they go. And the reason we want to do this is because imagine you have a probability distribution, you apply some sort of a procedure to it, which could be stochastic in general. You want to make sure that you have a probability measure when you're done at the output. So a positive map is exactly something that does that. It takes positive elements to positive ones. So if we have an algebra, but we're not using all of the structure of that algebra, we're only asking that positive elements go to positive ones. So it's sort of like an order preserving map. And a special kind of positive map has a codomain, which is just the complex numbers. And these positive maps will correspond to states. And the interpretation will be that you take your algebra element in A. So you take some A, which may correspond to, some random variable and observable in the setting of quantum mechanics. And then you apply this functional, you apply this positive map, and you get a complex number out. And if that element was positive to begin with, then this will give you an expectation value, which is a positive number. And so there are many examples, and let's start with the commutative setting first. So if you have a state on a compact Hausdorff space, on the algebra functions of the compact Hausdorff space, then that corresponds to a regular probability measure on the underlying space. And when you compute the value of that state on some function, then you're essentially computing literally the usual standard expectation value in the sense of probability theory. So I've just drawn a little cartoon on the right that sort of depicts, what's going on. You have this probability distribution P on some interval. You have some function phi, which in this case is just it looks like an identity map of sorts. I guess I'm thinking of X as, literally an interval. And then the expectation value is just going to be some number. And I've sort of tried to sketch what that number could be in this case. But now for matrices, if you give me a state, so this positive map into the complex numbers, then there exists a unique matrix which is positive and its trace is 1. So that satisfies this equality at the bottom here. So when I evaluate any element A, any matrix A with respect to that state, then it's as if I take that density matrix, multiply it with rho, and then compute the trace. Now, if you've never seen density matrices in quantum mechanics before, a very special case might ring a bell. So in this case, if you have a rank 1 projection onto the span of some vector, then the expectation value of that observable A, the value of that state on A, is exactly what you would have seen in a Quantum 101 class, where you take your observable A, you take your vector, then you compute this inner product, and that's telling you what the expectation value is of that observable. Now, besides just states, there are also many maps that you can construct if you have commutative algebra. So if we have, so more examples of positive maps. If we take a positive map between commutative algebras, they always correspond to a stochastic map on the underlying spaces. So to see why this is the case, if you give me an element of that underlying space on X, then we can construct a canonical evaluation map on the set of functions on X, which says essentially, if you give me any function on X and then a point on X, then I can just evaluate that function at the point X and get some number. And that's clearly a positive map, because if we take a positive function and then we evaluate it at some point, well, it's going to be positive there by definition. And it's also unital, because if we take the function 1, then we get out an output as just giving the number 1. So it's clearly a positive unital map. And we'll talk about more of the properties of this map later, but for now we can use it for understanding what a positive map looks like between commutative algebras. And if you notice, if we take the composite of that evaluation map and the original positive map F, then that gives us a positive map from the algebra functions on Y into C. So we get a state on Y instead. But if we take for granted the fact that states correspond to probability measures, then in what we get as a result of this is for every point in X, we get a probability measure on Y. And that's what we think of as a stochastic map. And now if we evaluate that probability measure on a specific point Y, and now I'm thinking of these as discrete sets, then that gives me a conditional probability of the event, for instance, Y happening, given that the event X happens. So we get this relationship between positive maps on commutative algebras and stochastic maps or conditional probabilities on the underlying spaces. Now, let's slightly elevate this example into the non-commutative framework by assuming that what if the domain is necessarily non-commutative? So let's just assume that it's a matrix algebra. And it turns out that a map of this form corresponds to an ensemble of quantum states. Now, if you think of the English word of ensemble, you're thinking of like a collection of quantum states. So why would this correspond to that? Well, we can use the same idea that we just did in the previous case. For each element X, we get some evaluation map. And when we compose the two, then we get a state on that matrix algebra. So for every element in X, we get a density matrix. And here I've drawn a little cartoon about what that looks like when M equals 2. And when M equals 2, then the collection of all density matrices, you can think of it as being, homeomorphic to a ball, a unit ball. And what this map is essentially telling us, this positive map is saying for each element in X, I'm going to choose, some collection of elements inside this, what's called this block ball. But in general, it's a much more complicated object. Now, there are plenty of other examples too. What if we change the codomain of our positive map and we kept the domain as a commutative algebra? Well, that will correspond to a measurement. By the way, if you hear that sound, that is the sound that it's like a remnant of World War II, I believe, in France, that they play every Wednesday morning around this time. So apologies for that, but it's quite short. So a measurement exactly corresponds to such a positive map. And why is that? Well, now instead for each element x, we look at the evaluation map at x. We can also look at the function on x that sends each element to either 0 if it's not x, or 1 if it is x. You can think of this as like a discrete version of a Dirac delta distribution. And so we have, because x is finite, you always have this function, and you can look at where this element goes under the positive map. So if we say that this element goes to some matrix mx, and then we take the unit, and then we know that it's a positive matrix, first of all, because that function is positive, right? It's always at least greater than 0 at every point. And not only that, but if we take the sum of those elements, because the sum of each of these Dirac deltas is equal to the unit element 1, then we know that that has to also go to the unit matrix 1. And if you've ever seen the definition of a positive operator valued measure in quantum information theory, quantum mechanics, this is exactly what it is. It's a collection of operators, positive operators, whose sum equals the identity matrix. Or it's also called a POVM. And a special case is when each of these is a projection. And this corresponds to a measurement of some observable. So for example, if we have a light emitter, and we can, let's say we're trying to, detect some kind of a polarization. Let's say it's, in the up direction or down direction, or north, south, east, west. We can apply this measurement and then determine whether that light emitter is emitting in either of these directions. And the matrices that correspond to these projections are exactly telling us about this measurement. Now, those are all positive maps. And I mentioned this evaluation map, which is an important one in the setting of classical systems. Another special kind of map that we can consider besides positive maps, they're more restrictive, and they're called deterministic. And deterministic maps just correspond to star homomorphisms of your algebra. They're just maps that actually, they don't just preserve the order structure of positivity, they also preserve the algebraic structure. And if they preserve the algebraic structure, we can try to understand, what do they correspond to on the underlying spaces of our if we have a commutative algebra, and these exactly correspond to deterministic functions. So these are these are stochastic matrices whose value at every point is a Dirac delta distribution. And then if you try to analyze, what does that map actually do to functions? Well, it turns out it's just the pullback. So rather than this expectation value function, it reduces to this pullback function. And as a special case of this, a deterministic map from commutative algebra into C, and this is also true even in the compact Hausdorff setting, corresponds to a Dirac delta distribution. So in other words, the stochasticity is exactly what happens when, with the lack of determinism. You can think of it this way. But these were classical systems. And let me just emphasize the distinction between these two types of states. You can either have states that correspond to, so I'll use states, evidence, belief, knowledge, all of those words interchangeably from now on, because these are the kinds of words that are used when we'll talk about Bayesian inference and Bayesian updating. But whenever we have states, you can view a state as either being hard evidence or soft evidence. And the example I just gave of these Dirac delta distributions, I'm going to think of those as hard evidence. And the reason is because there's no ambiguity about what state you're in. I know exactly the probability distribution, and not just do I know what it is, but it has a unique value. There's no variation. And soft evidence is essentially anything else. So actually a probability distribution that does have some spread. And there's a big distinction between classical and quantum, you can think of them as classical and quantum states, is that quantum states do not admit hard evidence in this sense, and all evidence is what's called soft. And in particular, you might have thought that maybe pure states should be considered as hard evidence, but that's not necessarily the case. And the reason is because you can make different measurements on a pure state and get probabilistic outcomes anyway. And that's actually quite different between the classical and the quantum setting. So this is kind of why I want to distinguish, pure states from hard evidence are quite different concepts. hard evidence in this sense, in the sense of determinism, does not exist in the quantum setting. And I'll come back to that when we discuss examples in a moment.
Can I ask a question?
Sure.
So this notion of hard evidence, you strictly speaking, you tie it to this notion of determinism, right?
Yes.
But how would you interpret the common property of deterministic classical states and pure quantum states, which are being these extreme points in the state space?
Right. Yeah. So exactly. I mean, that's exactly what they would be. You could consider them as being extreme states. And others, you can think of them. There's like a formal definition of what it means to be a pure map, and they would correspond to pure maps. So in this case, it turns out that hard evidence in the classical setting coincides with this notion of purity. And then when you generalize to the quantum setting, you have these two different properties, and one of them gives you one definition and the other one gives you another. So you get pure states in quantum mechanics or hard evidence, and those two definitions don't agree.
Okay, all right, thank you.
Thanks for the question. So the last thing before mentioning Bayesian, what it means to do Bayesian, what it means to apply Bayesian updating in non-commutative probability or probability theory, is this notion of almost everywhere equivalence. And I'll just briefly mention this because I don't think I'll be using too much of it throughout the talk. But if you happen to ever have things that are measure zero, this sort of notion is very important, right? If you don't have probability measures that don't have full support, in general, it's important to keep track of this information. And Bart Jacobs and Kenta Cho came up with this definition of this string diagrammatic definition of almost everywhere equivalence. And I've drawn the string diagram here, and I've written what that equation looks like in the setting of states on algebras. And it turns out, if you're looking at this kind of equation, it's maybe not necessarily easy to check, because you have to, let's say we have an m-dimensional algebra and an n-dimensional one, then we would have to check n squared, m squared equations, or n to the fourth if they were the same. And there's actually a theorem that simplifies this criterion a little bit. And the theorem says that if the two are equivalent, this notion of almost everywhere equivalence is the same as checking, you only have to check on one algebra. You plug in all the, let's say, unit matrices in that algebra, and you check if this condition holds. So you take the difference of these two elements, and then you square them, and that gives you a positive element naturally, and then you apply omega. And if that difference is always zero, then you know that your functions, your positive maps, are almost everywhere equivalent. And, if I, you might wonder, like, what does this have anything to do with if I take, like, two functions and I check, are these two functions almost everywhere equivalent with respect to some probability measure? It turns out it exactly reproduces that notion. So I've just done this little, like, mini calculation here and how you can use this theorem, right? If I have commutative probability spaces and then two stochastic maps, non-commutative algebras and, commutative algebras and stochastic maps between them, and a probability measure, then the two are almost everywhere equivalent if and only if, and I'm literally using this theorem here. I'm just rewriting the notation using integration, for instance, or you can think of integrals as sums too. But it says that the difference of these two numbers has to always be zero, because this is non-negative, exactly when this probability distribution does not vanish. So that's exactly telling you the two associated stochastic maps give you the same probability measures for all elements in the domain that have non-negligible probability. Now, with all of this information in mind, the notion of positivity and almost everywhere equivalence and states, we can make sense of Bayesian inversion. And I'll also use the lingo from statistics often in the talk. So I'm going to combine those together so that you can see the comparison. So if you give me a positive map between algebras, which is I'm also going to call that the likelihood. And if you give me a state on A, now note, it's very important that this state is on A, which is the codomain of this function. And again, because we're in the Heisenberg picture, I'm thinking of these arrows if I think of time, I'm going to think of them as going in the opposite direction. So, you pull back states, but you push forward probability measures. So if we have a likelihood and a prior, then you can pull back that prior onto the algebra B. This is sort of like, you can think of this as like an evolution happening. And we're going to call that the marginal likelihood. But these are all the data you need. You just need this map F and you need the state omega. And with that, you can define what a Bayesian inverse is of that pair. And it's a positive map in the opposite direction. So you can think of this as sort of like a time reversal, satisfying this strange looking equation, which is, oddly enough, very closely related to the notion of almost everywhere equivalence. And we sometimes even call this Bayesian inverse the posterior. And the reason this is so closely related to Bayesian, to almost every equivalence, well, you can actually show that when a Bayesian inverse exists, or if you have any two Bayesian inverses, then they're necessarily going to be almost everywhere equal to each other. So you can sort of think of like these two definitions as going in hand. And it tells you about the almost everywhere equivalence tells you about the uniqueness of these Bayesian inverses. So for example, if I took commutative algebras, I want to make sure that this reproduces something related to Bayes' theorem, right? So if you take just the algebra of functions and we take the correspondences between these positive maps and stochastic maps, I can write down exactly what this equation looks like in terms of those probability distributions. And it takes, I guess it's hard for me to highlight this, but it takes this form. Like I've literally just taken this and replaced it with the probability distributions. And I've chosen very specific elements for A and B. I've taken indicator functions on specific subsets of my space. So these are the functions that take the value 0 outside of your subset and 1 on that subset. And if I were to write this in terms of sums, it would look like something on the right, if you're not comfortable with the integral notation. But we can rewrite this by just changing notation around a little bit, and maybe it will look something familiar. It actually takes the form of ordinary Bayes' rule. So ordinary Bayes' rule tells me, if I have events A and B, then the probability of B given A times the probability of A equals the probability of A given B times the probability of B. So, by just changing notation around, we exactly reproduce the standard Bayes' rule from this definition. Now, what can you do with Bayesian inverses? Well,
Sorry, can I slow down you a little bit?
Sure.
If you go back to the slide.
Mm-hmm.
So this this formula that you wrote earlier using omega and xi.
Yeah.
Right. So this is the quantum analog of the Bayes rule that you wrote down.
Yes.
Highlighted in pink.
Yeah.
So so A and B are like the so you could classically interpret them as projections onto different events, right?
Yes.
Right. Okay. So what is F in the classical formula then?
Oh, F usually corresponds to some like some conditional probabilities. Like, there's this standard clinical type example where if you, let's say you have a collection of potential diseases or something like that, and with each disease, you have a certain probability of getting this or that symptom, right? That would be your map F. Well, that would be the map lower script F. And then the map lower script F bar would be the sort of the opposite, which says, if you give me a certain collection of symptoms, can I deduce what kind of disease you might have?
Okay.
Sort of like in the opposite direction.
So the thing that's inside the F, that is just to translate it to the notation with the
Yes.
Relative probabilities. So P of B given A. So the given A, that's what should be inside the F, or vice versa.
Yeah. So exactly. So okay. So the expression P of B given A is coming from mostly the information of the forward direction that I mentioned. So if you give me the disease, what are the probability distribute, like what probabilities, what symptoms could I get with what probabilities?
Yeah, so the disease is A.
Yeah, exactly,
Okay.
exactly.
And so that would correspond to what's on the right of the quantum formula. So F bar of A.
But that would be on the right-hand side.
Okay.
F bar is going in the opposite direction.
Okay.
Yeah.
Okay. I see.
Yep. Yeah, I've tried to do it so that, you know, it goes from A to B. So it's like kind of like A is the thing you know and B is the thing you're trying. Sorry. Yeah, A is the thing you know and B you can predict. But now if you're given something like that happens later or something, you know, something else, and you want to predict, you know, what is the likelihood of A happening? So yeah, also a lot of these things happen in that order, like A to B and X to Y. So I hope like that kind of like order helps keep track of things. I know notation is really important, but it is hard to keep track of all the, you know, different notations going on.
Okay, all right, thanks.
But, you know, I do think, I mean, as a non-probabilist, I think it's easier, you know, or more like along the lines of a mathematician, it's safer to not call something the same exact letter every single time, right? So that's kind of what I'm doing. I'm trying to give things different names because technically they're different things.
Just a moment after, so the existence of the Bayesian inversion, did you get, maybe I missed your condition because that is in, how to say, that is even in classical probability theory and statistics is not trivial equation, question, right?
Yeah, exactly. You don't have to worry, like in the classical setting for most reasonably nice spaces, you don't have to worry about whether this map exists or not. Sometimes it's difficult to compute it as a formula, but nevertheless, you know it exists. But you know, it's a little different question in the quantum setting, and I will get to that in a moment.
Okay. Thanks.
Yeah, thanks. But yeah, before I talk about the quantum setting, I want to just briefly talk about how you can use it to update information and hypotheses. So if you give me a prior and a likelihood, again, I can compute the marginal likelihood. You can then, and then also if you give me evidence. Now evidence, in this case, right, you have this patient that comes in and they have a certain amount of symptoms. That's, you can view that as your evidence. And then you have to, you want to basically make a deduction about, you know, and then let's say, you know, what their disease is, then you want to update what your prior is about, you know, the likelihood or prevalence of that given disease, for instance. And so if you know, algebraically, what you would do is you would take this Bayesian inverse that was associated to your initial prior and your likelihood, and then you would take this new evidence, and then you would get a new state on A, which replaces your prior, and therefore becomes the updated prior. And now it combines all of the information you had before with, you know, this expected stochastic map that corresponds to your probability distributions on like the prevalence of the likelihood of getting symptoms given a disease. And then you update your prior hypothesis, you know, on how prevalent that disease could be. And obviously you would do this after, you know, a larger data set.
Just a moment.
Yeah.
Okay, because on question, I mean, this in how to say, many people skeptic about the Bayesian statistics because of convergence, right? So you can have identify about the existence of convergence. You cannot take the in principle, you take any stage, you update. How it depends on the initial, yeah.
Yeah.
Yeah. So do you consider such a thing about the, how to say? You say that I updated because I believe it's correct, but you can. Do you really care about the convergence like in the statistic or classical statistic or not?
I mean, I think it depends on the type of question you're trying to answer. I think. Yeah, I mean, what you really want out of this is like in this clinical scenario, you generally want to make the best informed decision you can possibly make. And there are different measures of that and how you do that and different approaches. And this is just one of them.
So you just kind of, you take for granted that is the correct way, but you, how to say, because if you want really to do, for example, machine learning, yeah, you need to say that it really give you the, how to say, convergence
Right.
procedure, yeah.
Right, right. Yeah, no, I agree with that. But I'll try to stick to simple examples where these kinds of questions generally don't arise. These technical questions. Yeah.
Okay, thank you.
Yep, thanks. And so in this, let's take this particular example of, you have no idea, like somebody comes in with a coin and they're going to flip that coin. And they're going to do this experiment a bunch of times. And let's just say for whatever reason, you've never seen a coin in your life. So you have, you're going to make some assumption about the likelihood of it ending heads or tails. And you're like, well, I have no idea whether this is like a weighted coin, if it's more likely to land on heads or tails. And I'm completely agnostic about the whole situation. So you might associate some prior to that. And that prior could be based on the fact that you have no knowledge whatsoever. And you would call that like a uniform prior. So let's try to frame this in this algebraic setting. If I take my set Y to be heads or tails, or 0 and 1, and then I'm going to make my algebra B to be the set of functions on that. And I'll take the algebra A. In this case, it's going to be an infinite dimensional one. And I'm going to look at all the probability distributions on Y. Now, in this case, since Y is a 2-element set, that's a 1 simplex, which is isomorphic to an interval. And therefore, the algebra corresponds to functions on that interval. And therefore, if we take a probability measure on that space, that corresponds to a probability measure on the interval, which we can think of, in terms of densities too, oftentimes. And what we have is, besides just having a prior, right? If you come in and you're just like, I have no idea what the probability is, I'm just going to guess a uniform prior. Then you actually also have a canonical map between these two algebras in one direction. And this canonical map tells you that if you give me a function on Y, and I need to produce for you a function on the set of probability measures, well, if you give me a function on Y, and then you also give me a probability measure on Y, I can take the two together and I can compute the expectation value, right? So this actually gives you a canonical map that takes functions on Y to functions on the associated probability measures. This is sometimes called the sampling map as well, if you view it on the underlying spaces. And with these two things, you have all the ingredients you need to do Bayesian inversion or to do Bayesian updating, because all you needed was this prior and some canonical map. And we'll see that this is actually all you need to make some deductions about, coin toss experiments. Now, it's going to be easier for me to express all these terms in terms of the underlying stochastic maps rather than always thinking like this higher level in terms of the algebras of functions. So I might do that sometimes. But I'm going to pass through this pretty quickly, but just mention one thing, which is that if you give me this prior, and then you use this evaluation map, that gives you a probability measure on the space 0, 1 on the coin toss. And you can think of this as sort of combining all of your prior knowledge, your distribution on what you think could happen, and it gives you the end result, which is just tell me what the probability of tails or heads is, given that prior knowledge. And that's the barycenter of this probability measure. And using the Bayesian inversion formula, you can apply it to this pair, compute a stochastic map in the opposite direction. I've written the formulas here, but we won't be using them. I'll focus on the pictures more. And then if you give me evidence, we compose those two maps, and then we get some new probability measure on, again, this, it's like a second layer higher of thinking, and we get this probability measure on probability measures. That's the measure we're updating. That's the prior that we're going to be updating. And then so that's one coin toss, right? So the coin is flipped, you get a result, and then you see that as evidence, and then you update your prior, and now you wait for the next, experiment. So the coin is flipped again, and then you get an outcome, and now you use the new Bayesian inverse based on your updated prior, and then you keep iterating this procedure. But notice that it's always taking account of your new evidence. And this iteration of procedure is just, you compute Bayesian inverse, you get evidence, you compose. So everything is very compositional. And in our example, we can replace these things with, as I said, with density functions. Let's just work with that simple case. And let's just look what happens after we do this experiment a few times. So I'm actually reproducing something that I read in a paper of Bart Jacobs on this topic. If you've seen this before, that's where this comes from, and I'm trying to formulate it in this way and understand it. So let's say after a few experiments, we see the first coin toss gives us heads. Now, initially, we have this uniform prior of I'm not exactly sure what's happening. And then a coin is tossed and you land heads, and then you update. So you compose with that evidence with the Bayesian inverse of the initial map, and you get this new probability distribution. And you can see it's more weight towards the sides of heads at this point. But a second coin toss is made and you get tails. And now you take that evidence that you just had, and then you use the Bayesian inverse based on the updated prior, and then you get a new probability distribution by just following that formula and plugging and chugging and going through it. And you keep going through this. So you get let's say you get another tails, you get a third update, and then let's say you get a fourth tails, right? So you're getting heads, tails, tails, tails. You get a fourth update, and this is your new probability distribution. And you'll notice that it's getting a little bit more centered around some value, right? This width is decreasing as you do more and more experiments. And the idea is that, yeah, after you do enough experiments, you will eventually find out if this coin is fair, right? How fair is this coin? And right now it seems to be a little bit weighted towards tails, but of course you would have to do this experiment many, many more times to get a better idea of what is the associated probability distribution associated to that coin. So that was a classical example. We can also do a quantum example where this is going to seem to come out of nowhere, but imagine it's going to seem fabricated, in other words. So let's take the totally mixed state on 2x2 matrices. So that's just the density matrix 1/2, 1/2. And let's define this map F. So B transpose is you take the transpose, then you apply this weird matrix. It turns out this is a positive map. You can compute the marginal likelihood. It's also a totally mixed state, 1/2, 1/2. And then you can compute its Bayesian inverse. It also takes the same form, actually. And now suppose, so that's the setup, then you have the prior. And now suppose Bob, represented by B, obtains, again, it has to be soft evidence, and it corresponds to a density matrix that's, let's say, it's spin up, or you can think of this as polarization in one direction. Then you can apply this procedure, and then you can see what is the state that, you can think of this as saying, what is the state that Bob believes Alice will see or observe? And that corresponds to the density matrix for spin down. And this is actually closely related to the famous Einstein-Podolsky-Rosen scenario, where if you actually try to compute the joint state, I didn't describe what this definition is, how you compute a joint state associated to this, but it's kind of similar to, if you have two random variables and you want to compute the joint distribution, it's similar to this, so that setup. If you compute this joint distribution, you actually get the EPR density matrix. So it's one example, and it shows you that Bayesian updating, that this spooky action at a distance about what happens, when these states are correlated and entangled, the spooky action at a distance can also be viewed as just the form of Bayesian updating based on evidence. Now, that example was surely fabricated, and in fact, those maps were just positive, and you can't always implement them. In general, it's believed that you can't implement them as quantum operations, which are generally believed to be what's called completely positive. And these are special kind of maps that have more positivity properties than usual. Here's the definition, but you know, it's too many definitions, so I think it's better just to know that it's a stronger form of positivity. Now, if we assume that we have this stronger notion of positivity, and we have a map between these matrix algebras, so it should say let F be CPU, actually, completely positive unital, and we have a state, then we can, so we have a prior, we have this likelihood, and we have the marginal likelihood. And let's just also assume that we don't have to worry about measure zero events. So we'll assume that these states are faithful, or the density matrices have no zero eigenvalues. Just for simplicity, we can use these data to define a new map that goes in the opposite direction. Now, just by writing this map, you know, at first it's just a linear map. And in fact, it turns out to also be unital. But other than that, it doesn't have any special properties. But it turns out that it does have special properties. If it has some kind of special property, it has a lot of other special properties. So if it turns out that this map, G, sends self-adjoint elements to self-adjoint elements, then it turns out that that map is completely positive unital. And furthermore, there are a lot of other conditions that characterize what this is. And one of them is the fact that a Bayesian inverse exists for the map F. So it gives you a way of understanding when a completely positive map Bayesian inverse exists, given a prior and a completely positive likelihood. And this does not illustrate the previous example because that map was not completely positive. So this is a general theorem for when your maps are quantum operations. When can you implement your Bayesian inverse as a quantum operation? That's the question this theorem is answering. And when you can do that, it takes a very simple form. This form is sometimes called the Petz recovery map. And it takes this form, but when the density matrices are not invertible, you get in general a different map. And we have a statement for what that theorem looks like, but it is a little bit technical. So I'm not going to discuss on that. Rather, I want to discuss some of the special cases that occur. And that will be essentially the rest of the talk, special cases of that theorem. So imagine you have a star isomorphism between your algebras. And it turns out that the inverse is always a Bayesian inverse for any pair. So this is important because it tells you, okay, at least if I compute the Bayesian inverse of something that's a star isomorphism, then I get something that looks like the inverse. So it's very, good to know that it reduces to that special case that kind of also supports the name of Bayesian inverse. It also has a compositional property. And that compositional property says that if you can do successive Bayesian inversion, right, like in sequence, then to do the Bayesian inverse of the composite of that sequence, you can just apply the Bayesian inverses of each parts of that sequence in reverse order. So that's also a very natural property you would expect. If I'm updating things in sequence, then I want to make sure that that updating procedure also occurs in sequence with respect to that same sequence order. Now let's look at a slight generalization of the first example. If we have a deterministic map, so a star homomorphism, it turns out they always look like you take a matrix B and ignore the U's, and you take that matrix and you tensor it with some identity element. So it basically, it takes that element B and just repeats it a bunch of times inside of your larger matrix algebra. All deterministic morphisms look like this. And you can ask, well, if you give me a state on a density matrix, when does a Bayesian inverse exist for this scenario? And it turns out it's not always the case, but it is the case if there's another density matrix such that when you tensor your induced density matrix on B with that density matrix, then you reproduce the density matrix that your prior corresponds to. And this might look familiar if you've seen something like, if you have come across non-commutative probability. In this last example, the formula for the Bayesian inverse takes a very specific form in terms of like a partial trace. You write your codomain as a tensor product of two algebras, and then the map in the opposite direction is taking the partial trace of one factor. And this is exactly, it has a very nice property, which is when you map forward and you map backwards, you get back the identity map. So it sort of fixes a subalgebra. And maps that fix a certain subalgebra are called conditional expectations, at least in the non-commutative literature. And they're also called conditional expectations in the classical literature when you phrase it in terms of the appropriate algebras of spaces. And there's a more general concept that's applicable even when you have states of measure zero. There's states that have measure zero in them. And this happens more often when you look at direct sums of matrix algebras, or when you go to the infinite dimensional setting, where it becomes where measure zero plays a more important role. And in this case, you can turn this into a definition, this special kind of case. If you have a likelihood, and then you have this prior, then you can define a disintegration of F. And this is also a positive map in the opposite direction, but it doesn't satisfy exactly Bayes' theorem. It satisfies two other conditions, which is it preserves states. So you want to reproduce the state you started with, and it's like a left inverse. It's a left inverse up to sets, up to measure zero. And we discovered, you can think of this way of viewing it as, a consequence of a Bayesian inverse. So there's a relationship between these two concepts, actually. And it's quite subtle and interesting. If you start off with a deterministic likelihood and a prior, of course, and you have a Bayesian inverse of that with respect to that state, then that Bayesian inverse is of this type. It is a disintegration. So it does satisfy this left inverse property. And the proof of this is quite simple. I'm just going to show it here on the slide. It's a nice string diagrammatic calculation that just tells you immediately, oh yeah, I can see why this is the case if I just use the string diagrammatic definitions. So again, let me just repeat this because it's important also for the next slide. If you have a deterministic map that's Bayesian invertible, then it's disintegrable. You can take that Bayesian inverse and it satisfies these slightly stronger properties. There's a partial converse to this, which I think is a little bit less known, but known in special cases in the literature. And if you now start with a completely positive unitary map, a completely positive unitary likelihood, and then a prior, and then you obtain, let's say you have a disintegration of it, right? So not a Bayesian inverse, but a disintegration. Then it is a Bayesian inverse, but even more happens. It turns out that the only way this can occur is if F is not just completely positive unitary, but it's essentially deterministic to begin with. And this is just a technical definition that also includes the fact that it might not be deterministic exactly, but it's deterministic in an almost everywhere sense. So it's sort of like a no-go theorem. It tells you that the disintegration condition imposes more severe constraints on F than merely the Bayes condition for what it means to do Bayesian inversion. And this is important because it tells you that, in particular, it tells you that if you want to abstract in this order, right, you start off with invertible maps, and then you want to abstract that a little bit more, then you come up with disintegrations, these like left inverse type maps. And if you want to abstract that even more to include things like stochastic processes, then the one appropriate generalization of that notion is the notion of a Bayesian inverse. And these two theorems essentially tell you that in a rigorous manner. So let me talk about the last example I have, which is an error correction, and how this notion of disintegration naturally appears in the setup. And this is just going to be a very illustrative, not quantitative setup. So suppose Alice wants to send Bob a message across a noisy quantum channel. So here I've drawn Alice, here's Bob on the right. And what she does is she first encodes her state into possibly a larger space. And the reason you might want to do this is because, if you want to encode information and you want to preserve it under errors, then you generally want to do some kind of procedure that, increases the number of messages you could have, so that when an error occurs, it doesn't push you too far away from your message, and you can try to apply some procedure to recover it. So you can do this either classically or quantum mechanically. So again, the arrows might be confusing because I'm in the Heisenberg picture. You can try to reverse them so that you can see the directionality of the information flow. Now, so this is what Alice does. She encodes her state into a larger space, depending on what errors could occur. So she knows what kind of transmission channel she has, and she knows the possible errors that could occur. So she's going to encode her information in a certain way to account for that. But what Bob needs to do is Bob needs to, receive the message and then apply a procedure to first detect and fix that message. And then after that message has been fixed, then Bob has to decode the message so that it's, in the same form that Alice had sent it. Now, in this setup, Bob's recovery procedure needs to be deterministic. And the reason is because, there has to be a procedure involved, a specific procedure that tells you, if this outcome happens, what do I have to do? What does Bob have to do exactly to recover that information? It can't be a stochastic procedure. And it turns out that the error is the disintegration of the recovery map with respect to some state of, let's say, full support. And in this case, when you're viewing the problem in this way, in this language of disintegrations or Bayesian inverses, it says that the existence of a disintegration or Bayesian inverse aims to answer the question, what errors will the recovery procedure fix? So it's kind of like the opposite question of what you might do in a quantum error correction scheme, but it's still an interesting question to ask. Normally in quantum error correction, you know what errors will occur, and then you ask, what recovery procedure should I apply to fix those errors? Whereas in the case of whether a disintegration exists or not, answers the question, if I have a specific recovery procedure, what errors will that fix? So there are many questions. This is sort of like at its early stages. Categorical probability theory itself is at its very early stages, and likewise, the same thing could happen for. The same thing is true for quantum probability from this categorical perspective. And one of the things immediately is that this EPR example, we gave this example where the map was not completely positive, but just positive, and we don't know what Bayes' theorem says for just arbitrary positive maps. But clearly it's a little bit, it should generalize the theorem I had mentioned earlier. You might also ask, we constructed this EPR density matrix by some categorical procedure that generalizes the notion of taking two random variables and computing a joint distribution in some sense. And you want to know what states can be constructed in this way. So we don't know what the answer to that is at the moment. Another question is the error correction scheme I mentioned earlier is known for special cases or special assumptions, but in general you want to make sure it's known for all. And at present we don't know actually the full nil-Laflamme conditions, whether they hold or not for disintegrations. That's still an open question. And just abstractly, right, to what extent can you use Bayesian updating to outperform classical Bayesian updating procedures? And you might want to be able to determine states or something like this, or how recovery maps are used. Can you improve on classical measurement and then classically Bayesian updating something? And then finally, because of this advances in categorical probability theory, what theorems from that setting actually abstract to the quantum one? And do they offer, interesting proofs of old theorems, or can they also be used to prove new theorems in quantum probability? Of course, that would be, the most exciting thing that one of the most exciting things you could do. And with that, I'll end. I'll leave a lot of the references that I gave, or a lot of the references that I took from to make this talk. So I thank you for your attention.
Yes, thank you very much, Arthur. That's really interesting. I already have some questions. Yeah. Yeah. First, that's actually I also now discuss it. You say about you generalize the concept of the conditional expectation. Yeah, yeah. And actually, I know it that I mean that I also know how to read. Maybe I have not yet written explicitly in the appendix. I give you but a formula on this year. That means that's how to say, in classical statistics, people think that kind of Cohomology 100 years ago, they think that if you given some observable, I mean that even is interpreted in the sigma, sub-sigma algebra.
Yeah, exactly.
And then you have the conditional expectation, and that is related to measurable map. Yeah. But if you write the formula, that means that you can push forward under this measuring map. And the generalization is a probabilistic map, right?
Yes, exactly.
That's what I mean, that's I don't on formula, but I should add that interpretation in our thing. But the one thing is how to say, the thing is what is the interpretation in the kind of the, you cannot define sigma algebra under the probabilistic mapping, right?
Well, yeah, so even in the case of a sub-sigma algebra, you can think of this as it's like a measurable map, so special kind of stochastic map, right? Where you're going from, I hope I don't get this wrong, you're going from the sigma algebra with fewer elements into the sigma algebra with more elements on the same space. Use this
No, you cannot, because that is a thing that how to say that is I really I don't know that's I have the colleague who is interpret everything in terms of the classical statistics, and he say very simple. Why I make things so complicated? Formal, but with the formal things, and you can generalize very easily, but you don't know how to interpret it. And then in quantum case, so what is sub-algebra observable, and how you define the conditional expectation?
Well, yeah. So I mean, so in this case, you would think of so it's a deterministic map, but it's a special one, and it's one where it's just an injective star homology.
Yeah. But so not deterministic, then you say that you can like a conditional expectation, like how to say poorly formula, but you don't know how to interpret it. You can have some interpretation. For example, in quantum physics, that's maybe more interesting.
Yeah. So I mean, the point of let's see. I think the point of this theorem is that if you have this stochastic map and you have this conditional expectation, then that stochastic map, quantum or classically, but this is true for quantum mechanics or classically, had to be deterministic to begin with. So you're always talking about conditional expectations, essentially, if you're working in the setting of disintegrations. It's only when you remove that condition of satisfying this disintegration condition, which is similar to the conditional expectation condition. It's only when you remove that restriction and you allow yourself to instead use the Bayes condition, that's when you can allow for these stochastic procedures. And that's when you can allow, like, classically in this situation where you have disease and symptoms, that's not always the case. Like if you have one disease, then 100% of the time I'm going to get these symptoms or that symptoms. And in this case, you could think of like the conditional expectation would sort of tell you like, then that's all you're considering. But if you're allowing yourself to use Bayesian inverses, then you're allowing actually something that's much more realistic. You're saying, okay, well, I know that this disease can give this and that with a certain probability. It's not always the case, but I'm allowing this flexibility. And that's what you're achieving by generalizing from conditional expectations to this notion of a Bayesian inverse. Yeah, I hope that answered the question.
Yes, thank you very much. Yes, that's really, at least I'm very happy to listen, to learn something more and directly benefit to my current work. There are some more questions.
You had just a very general question. Arthur, you're using this term categorical probability or categorical approach to probability.
Yes.
But to be honest, at least in this talk, I don't see a lot of the category theory. So just wondering, what do you mean by that? And like, did you actually use any of it?
Yes, that's a good question. I generally try to hide that stuff under the rug. Because it does take a lot of time to develop all of it. But like, let me mention, well, let's like this diagram, for instance, here even. The idea is that you, one of the ideas is that you try to formulate a concept that you understand very well, right? Like something like Bayesian inversion or something. And then you try to express it in some abstract categorical language. You're trying to say, what structures do I need on a category to make sense of this rule or to make sense of this notion? And then you can ask the question, okay, now I have this structure and I want to know in which context does it apply? What other categories does the structure exist in and allows me to make sense of this definition? And if you naively apply the procedure for categorical probability theory in the quantum setting of algebras and positive maps, you run into a lot of problems. And the first immediate problem you run into is the fact that this copy map that I'm drawing here, sorry, this multiplication map that appears almost everywhere is not positive. And because of that, you might think, well, I can't really, whatever structures, where I didn't mention this, but like all of these probabilistic categorical probability theorems are proved in this setting of string diagrams and abstract probability theory. But if you wanted to instantiate them in the quantum setting, you have to make sure that you have a category that admits these structures. And if you just work with positive maps, it doesn't work. And so you generally have to like enlarge your category to include more than just positive maps. And that's where the sort of like, it's really in the instantiation part from the abstract categorical probability theory that I've mostly talked about today, rather than where does the probability theory come in? But I did mention these. So there's this theorem here, and I didn't write down the proof of this theorem, but you can also prove this theorem using string diagrams as well. Just like
so you're saying that so some proofs, once you find the right categorical yes. setting, the proofs lift to that level, and exactly. If you ever find a different category that satisfies the same axioms, you can reproduce it there.
Exactly. The only reason I illustrated this one is because the proof is so simple. For this one, I think it's well, first you have to prove that a certain category satisfies some categorical axioms. And then once you know that, then the proof of this is completely string diagrammatic. It's just a few lines more than the previous one. Yeah, exactly. And that's really the whole, like, sort of like one of the major ideas is to, find out the key axioms you need and then prove the rest, prove the rest of probabilistic theorems just using string diagrammatic techniques.
Okay, thank you.
Okay. So let us thank the speaker again if there are no more questions. Yeah. Okay, thank you very much, Arthur. Yeah. Then